Welcome to the Walton Pi. Today we're going to be talking about differential equations, specifically exact equations, what they are and how to solve them. So first we're going to discuss a little bit of a connection to multivariable calculus. So let's suppose that we have a function big F, which is in terms of both x and y, where y is also going to be considered a function of x. If we were to take the derivative of f with respect to x, then the chain rule is going to give us terms both with a y prime and without a y prime. So for example, let's suppose that f of x and y was 3x squared times y to the fifth. If we took the derivative of f, then we would get 6xy to the fifth plus 15x squared y to the fourth times y prime, which has a term both with a y prime and another term without a y prime. So if we had the differential equation 6xy to the fifth plus 15x squared y to the fourth y prime equals sine of 3x plus x cubed, how could we use the information that we know to be able to solve this? Well, we just figured out that 6xy to the fifth plus 15x squared y to the fourth y prime is the derivative of 3x squared y to the fifth. So we could integrate both sides of the equality to get 3x squared y to the fifth is equal to negative cosine of 3x divided by 3 plus x to the fourth divided by 4 plus c. And then since we are wanting to solve this differential equation for y, we can then solve this for y to get y equals the fifth root of negative cosine of 3x divided by 9x squared plus x squared divided by 12 plus c over x squared. We would be able to get that just by dividing both sides by 3x squared and then taking the fifth root. So if we can find a way to consistently recreate this process we just went through to solve differential equations that look like this, we're going to have a method to solve certain types of differential equations. So these types of problems are what are called exact equations. But how can we tell if a given differential equation is an exact equation or not? Well, for this, we're going to go back to multivariable calculus and remember that the derivative of f with respect to x and then y is the same as the derivative of f with respect to y and then x, as long as the partial derivatives are continuous. So we're going to use this fact to determine if a differential equation is an exact equation or not. So if we begin with a multivariable function f, then any exact equation derived from this function is going to be of the form f sub x plus f sub y times y prime equals g of x. And this is coming just from taking the derivative of f. The chain rule is really just saying take the derivative with respect to x, and then take the derivative with respect to y, and then deal with all of the y prime terms. So to check if a differential equation m of x and y plus n of x and y, y prime equals g of x is an exact equation, we just have to check whether or not m sub y equals n sub x. Because the m piece, that's going to be the part of the function that didn't have a y prime on it, so that's the f sub x part. And the n piece, that's going to be the f sub y piece. So we take the derivative with respect to x, and if they match up, then there is that original function big F somewhere. So if they're equal, you have an exact equation. But if they're not equal, then you don't. So if m sub y does not equal n sub x, you're going to have to find a different method. But in that case, hope's not quite lost, because if you don't have an exact equation, integrating factors turn the problem into an exact equation. So you can be able to go and figure that out. And if you need a little refresher on what integrating factors are, go ahead and check out this video that will be showing up in the card right about now. So now let's go through an example of solving an exact equation. So let's suppose that we want to solve y squared plus 2xy squared plus 2xy plus 2x squared y plus 3 all times y prime is equal to 5x to the fourth. When we check to see if this is an exact equation or not, we take the derivative of y squared plus 2xy squared with respect to y, and we get 2y plus 4xy. And then if we take the derivative of 2xy plus 2x squared y plus 3 with respect to x, we also get 2y plus 4xy. So because those match, this is going to be an exact equation. So then to find the function f such that f sub x is that y squared plus 2xy squared, and the f sub y is the 2xy plus 2x squared y plus 3, we can integrate both pieces with respect to x or y respectively. Once we've done that, we just need to compare the two to find a function f that's going to work for what we need it to. So let's go through this example. So we have our differential equation. It's the same one that we were just talking about. And since we know it's exact, we can do the following integrals. The integral of our piece without the y prime with respect to x. And when we do that, we get xy squared plus x squared y squared plus some function that was only of y's. Now the reason we have to have that function of only of y's, we don't know what it is yet, but we need that because if we were to take the derivative of a function with just y's, that's going to disappear. And so that's why that piece is sticking around. And then we're going to integrate the piece that was attached to the y prime with respect to y. So we integrate 2xy plus 2x squared y plus 3 dy, and we get xy squared plus x squared y squared plus 3y plus some function only of x's. Note that these two functions nearly match up, and so if we grab each unique term that appeared anywhere, we get xy squared plus x squared y squared plus 3y, and there we go. Now notice we don't have any pieces that only had x's in it, but we did have that 3y appear. That 3y is the g of y in the first equation. Now, this is just a coincidence that we didn't have an h of x term anywhere. Sometimes you would, and so you'd have to go through and deal with all of that. But that means that that is going to be the integral of our left-hand side of our differential equation. So that means that we have, as our solutions, xy squared plus x squared y squared plus 3y equals the integral of the other side, which is x to the 5th plus c. And anything that satisfies that are going to be our solutions. Then it's just a matter of, can you try and solve for y, and then that would be how you would finish out this problem. So I hope that made sense. I hope exact equations are a little bit clearer as to what they are and why we do what we do. If it was, please consider leaving a like and subscribing. It really helps me to keep making these videos. I hope you have a great rest of your day, and good luck with the rest of your math.